Welcome to the third part of Module 6 of C203 Fluid Mechanics 1. In this video, we'll be discussing the problems from Module 6. So we have identified 6 types of problems. So in this video, we'll be discussing only the first 3. Okay. So we'll just discuss the different types. First type is U by U will be given, that is the velocity profile will be given, and we have to find out delta star, theta and delta double star. The second type, we need to derive or we need to find an expression for delta tau naught FD in terms of Reynolds number when laminar velocity profile is given. So laminar velocity profile, that is U by U, will be given. You have to find out the expression in terms of Reynolds number for these terms, that is type 2. Then in type 3, we need to find the numeric values of delta, tau naught, FTCD, etc. when velocity profile and the values of L, B, U, mu, etc. are given. So in type 3, you have to find out the numeric values, and in type 2, you have to derive an expression for these terms. Okay. So these type 3 can be done only if you memorize the equations for these terms. Okay. So these 3 types will be discussed in this video, and the remaining will be discussed in the next video. So we'll first discuss type 1. Yeah, before that we need to know about Reynolds number. You all know that Reynolds number for the total length of the plate which is kept in a moving fluid, REL is equal to rho UL by mu, where rho is the density of the fluid, U is the free stream velocity of the fluid, L is the length of the plate which is introduced in the moving fluid, and mu is the coefficient of viscosity of the fluid. Okay, so this is for the entire length. For the entire length, or at the end, what is the Reynolds number? If you are considering a section in between, then you can express the Reynolds number as REX. Okay, so in some equations you will be finding REX. In some equations you will be finding the term REL. What is the difference? REX is at a particular section, which is at a distance small x from the leading edge, if you consider a thin flat plate, and REL means it is at the end. For the total length, what is the Reynolds number? Okay. Now this mu by rho can be written as nu, where nu is the coefficient of kinematic viscosity. Here mu is the coefficient, this mu is the coefficient of dynamic viscosity, and nu is the coefficient of kinematic viscosity. Okay, so you can use these two equations for finding REL. So now we'll discuss type 1. In type 1, as I told you, U by U, that is the velocity profile will be given. We have to find out delta star, theta and delta double star. So we have already studied equations for delta star, theta, delta double star. So you just have to apply those equations. So this is an example. Find the displacement thickness, momentum thickness and energy thickness for the velocity distribution in the boundary layer given by U by U is equal to Y by delta, where U is the velocity at a distance Y from the plate and small u is equal to capital U at Y is equal to delta, where delta is the boundary layer thickness. Also calculate the value of delta star by theta. So you have to find out delta star, theta and delta double star. You have the equations. This is a question. So this is of type 1. How to identify whether it is type 1? You have to see whether U by U is given or not. Here small u by capital U is given, and we need to find out delta star, theta and delta double star. So this is of type 1. Now how to apply equations? We are writing the given details. Velocity distribution U by U is given. This is the value. Now displacement thickness delta star is equal to integral 0 to delta 1 minus U by U dy. This is the equation. So to this equation we will be substituting the value of U by U, and then we'll be integrating in order to get the value. So substituting the value, then we integrate Then applying the limits, we'll be getting the value of delta star as delta by 2. Okay, so we got the value of displacement thickness delta star. Now we'll move on to theta. The equation of theta, momentum thickness theta is equal to delta integral 0 to delta u by u into 1 minus u by u dy. So in this equation, we'll be applying the value of u by u, and then we'll be integrating this equation, and you'll be getting the value, apply the limits, and you'll be getting the value of theta as delta by 6. Okay, so you got displacement thickness and momentum thickness. Now we'll go for energy thickness. Energy thickness delta double star is equal to, the equation is integral 0 to delta u by u into 1 minus u square by u square into dy. So substitute the value for u by u and then integrate this. On integrating and applying the limits, you'll be getting delta double star as delta by 4. Okay. Now in the question, one more data is asked. We need to find delta star by theta also. So from the value that we obtained, we can find out delta star by theta as 3. Okay, so this is how you do type 1 problems. Very simple. You have the direct formula, substitute the value of u by u and integrate. You'll be getting the answer. So this is type 1. Now we will move on to type 2. In type 2, as I told you, we need to derive an expression for delta, tau naught, FD and CD. What is delta? Delta is the boundary layer thickness. Tau naught is the shear stress at the boundary of the solid surface. FD is the drag force and CD is the coefficient of drag force. So, and all these expressions will be usually asked to find out in terms of Reynolds number. Okay, so we'll consider a question. For velocity profile for laminar boundary layer, u by u is equal to, this expression is given. Determine the boundary layer thickness, that is delta, shear stress, that is tau naught, drag force, that is FD, coefficient of drag is CD. So you have to find out these terms in terms of Reynolds number. Okay, velocity profile is given, u by u is given. Okay, so if these two conditions are satisfied, that is, if laminar velocity profile u by u is given and if you are asked to find out these terms, then it is of type 2. How to do this problem? So we'll first write down the given data. U by u is equal to 3 by 2 into y by delta minus 1 by 2 y by delta cube. Now we have already studied the momentum equation, tau naught by rho u square is equal to dou theta by dou x. We have already studied this in the previous video. So here theta, we know that it is the momentum thickness and we have the equation of theta. See, the equation of theta is integral 0 to delta u by u into 1 minus u by u dy. So we will be substituting this equation for theta. So you will be getting the new equation like this. And now in this equation, we can substitute the value of u by u. Okay. So we are substituting the value of u by u in this equation. And we are simplifying, opening all the brackets, and then we integrate. We have an integral sign over here, so we integrate with respect to dy, and then we apply the limits. We simplify the terms. Only simple integration is used over here, and finally the equation becomes tau naught by rho u square is equal to 39 by 280 into dou delta by dou x. Okay, so that is the equation that we'll be getting. So we got an expression. In the previous slide we got tau naught by rho u square. Now what I'm doing is I'm taking this rho u square to the other side in order to get an expression for tau naught. So I got the expression for tau naught as this one. Okay, so that is the first expression for tau naught. And this is obtained from the momentum equation. Now I have another equation which is based on Newton's law of viscosity. What is Newton's law of viscosity? Shear stress is directly proportional to the velocity gradient, and the coefficient of proportionality is mu. Okay, so based on that, based on Newton's law of viscosity, we have another equation for tau, that is tau naught is equal to mu into du by dy at y is equal to 0. So this equation for tau naught is based on Newton's law of viscosity, and this one is obtained from momentum equation. Okay, now in this equation we'll be substituting the value of du by dy. We know that u by u is already given in the question. Okay, so from that equation you can write small u is equal to, taking capital U to the other side, you will be getting this expression. And now we are going to take the differential of this equation, so that we'll be getting the term du by dy. Okay, so differentiating this equation, you'll be getting du by dy, differentiating with respect to y. Okay, now we are substituting the value of y as 0 because we need the term du by dy at y is equal to 0. So in this equation, substitute y is equal to 0 and you'll be getting the value for du by dy at y is equal to 0. Now we can substitute this value in this equation. Okay, when you do that, you'll be getting a new equation for tau naught, and this is the new equation for tau naught. So this is equation number 2. So we got two equations for tau naught. The first equation is from momentum equation and the second equation is from Newton's law of viscosity. Now we are going to equate these two, equation 1 and equation 2. Equating these two, you'll be getting this expression, and here after rearranging, on one side you have delta dou naught, dou delta, and on the other side you have dou x. Okay, so here you have dou delta and on the other side you have dou x. We can integrate. So on integrating, integrate this side with respect to delta and this side with respect to x. Now on integrating, we will be getting this expression, and in order to find out the constant, integration constant, we need to apply boundary condition. So when x is equal to 0, delta will be equal to 0. What is x? If you consider a plate which is introduced in the flow field, you will be having the boundary layer thickness at the leading edge as 0. That means at the leading edge where the boundary layer formation is starting, at that particular point the boundary layer will be just starting. So the thickness of boundary layer will be 0. That is the boundary layer, that is the boundary condition that we are going to apply in order to find out C. So when we apply this to this equation, you will be getting the C value as 0. So the equation becomes delta square by 2 is equal to 420 by 39 into mu by rho u into x. So this is the equation. On rearranging, you will be getting delta is equal to this term, and here we have already studied what is Re or Reynolds number. Reynolds number Re is equal to rho u x by mu. So here you have the Reynolds number. So in the denominator you have root Rex. Okay, so why is it Rex instead of Rel? Because in this expression it is rho ux. If it was rho ul, it would have been Rel. But here it is rho ux. So it is Rex. So the expression of delta in terms of Reynolds number is given by 4.64 x divided by root Rex. Okay, so you got the expression for delta. Now, we got the expression of delta. We are substituting that delta in equation number 2. What is equation number 2? It is obtained from Newton's law of viscosity. To that expression, we are substituting the value that we just got, and you got a new equation, and this equation is in terms of Reynolds number, and this equation is for tau naught. So second part of the question is also over. First we got the expression for delta. Now we got the expression for tau naught in terms of Reynolds number. Now we have already studied in the previous video that the expression for drag force Fd is equal to integral L0 to L tau naught B into dx. So using this we are going to find out the expression for Fd. So here we'll be substituting the expression for tau naught and we'll be integrating and simplifying. Here only unknown is x. So you can easily take all the constants outside the integral sign and you just integrate this and you'll be getting the expression as this one. Okay, so we got the expression for Fd in terms of Reynolds number. Here, yeah, look here it is rho ul by mu. So here you can write REL. Okay. Now here it is REL. We also know that CD is equal to FD by half rho AU square. We have already studied this equation. So area A is nothing but length into breadth of the thin plate. Substituting that value, you will be getting the expression for CD also in terms of REL. Okay. Fine. So we got the expression for all the terms in terms of Reynolds number. This is how you do type 2 problems. Okay. So this problem is done for the velocity profile which is already given. The velocity profile given is going back. Okay. So this is the velocity profile given in this particular example. So like that we can have different velocity profiles. So I have referred and I have compiled the equations that's obtained for different velocity profiles. Okay, so this is the procedure. Yeah, see in this table I have compiled the values obtained or the expressions obtained for common velocity profile that is asked for the examination. Okay, so these are the few velocity profiles that are usually asked, and these are the values of delta, tau naught, Fd and Cd that is obtained. Okay, now this is how you do type 2 problems. Now in type 3, as I already mentioned, we have to use the equations. Velocity profile will be given and the values of x, u, mu, etc. will be given. So if you know these formula, you can easily find out the numeric values of delta, tau naught, Fd, Cd, etc. So in type 3, we need to find out the numeric values. So we'll see some example. We'll see an example. Type 3, find the values of delta, tau naught, Ft, Cd when velocity profile and these values are given. Okay, so you need to memorize the table which I showed you in the previous slide. Then only you can do type 3 problems easily. Otherwise, you will have to sit and derive the formula, but that is not possible in the examination. So you need to memorize the table. So here this is an example. Velocity profile is given. You have to find the thickness of the boundary layer and shear stress 1.5 meters from the leading edge of the plate. The plate is 2 meter long, so L is equal to 2 meters, 1.4 meters wide, that means B is equal to 1.4, and it is placed in water which is moving with the velocity of 200 mm per second. So this is free stream velocity U. Find the total drag force on the plate if mu for water is 0.01 poise. So we'll first write down the given data. Velocity profile is given. Distance x from the leading edge. X is equal to 1.5 meters here. See, this is 1.5 x. Length of the plate L is equal to 2 meters. Width of the plate B is equal to 1.4 meters. Velocity of the plate is given in mm per second. That is converted into meter per second. Then viscosity of water mu is equal to 0.01 poise. It is given in poise. We have to convert that into Newton second per meter square. So dividing by 10, we will be getting the value in Newton second per meter square. Okay. Now As I told you, we need to memorize this table. We have to find out which velocity profile is given, and corresponding to that velocity profile, we have to choose the equation for delta, tau naught, Fd and Cd. Okay. So here I have just displayed the equations. So based on the equation, we can find out the value. So in all the equations, we have Reynolds number. So first we need to find out the value of Reynolds number. This is the value of Reynolds number. Now take the expression for delta. This is the expression for delta. Substitute the values and you will be getting the answer. If you memorize the equations, it is very easy. But it is a little difficult to memorize the equations. So just take the equation for tau naught, Fd and Cd is not asked in the question. You just need to find out the total drag force. See, Fd is not the total drag force. It is the drag force on one side of the plate. So on the other side also you will be having the same value. So in order to find out the total drag force, you need to multiply Fd by 2. Then only you will be getting the total drag force. So total drag force is equal to drag force on both sides of the plate. That means 2 into Fd. Fd is 0.1138. Substitute the value, you will be getting the total drag force. So this is how you do type 3 problems. So we have discussed type 1, type 2 and type 3. And in the next video, we'll be discussing the remaining types of problems. That is type 4, type 5 and type 6. Okay. Thank you.